Hello everyone, welcome to a physical science lesson, and today we're doing something really exciting. We're going to be revising chemical change. Now, chemical change happens all around us, and you know what? One of the reasons why we're studying this is because it's such a big part of a chemistry assessment. So let's go in and see what you need to know and what you need to remember. So when we look at chemical change, we must recognize that there are different components of this chemical change. And the first thing that we will notice is we're looking at energy and change and how that relates to each other. We're then going to look at the rate and extent of reactions. We need energy to make the reaction happen, and we're going to see how that works together. Now, obviously, when we're doing these sorts of things, we can get different types of reactions. And I've listed some of them here. You get acid-base reactions, you get redox reactions, you even get organic reactions. Now, all of these also lead to some calculations, which you know we call stoichiometry. We're not going to be doing any stoichiometry today, and we're not going to do organic or redox, although these ones also link to that very special type of reaction called a system in chemical equilibrium. So those are the things that we're going to focus on. We're going to tie some ends together, because sometimes in a test or exam, you could get these concepts linked together. We're going to spread them apart and separate them and just focus on what you need to know and give you a few examples and tips and strategies of how you can best prepare for a chemistry assessment. So let's go to our first topic, which is on energy and change. And the thing that we want to talk about, which is really important, is heat of reaction. Now, there's another word we can use for this. It's called enthalpy. And you might see that coming across. We will define it. The easiest way to look at these terms under energy and change is to look at something called an energy profile. Now, I know that you are immediately saying, oh, what's an energy profile? Is that something we do in art, where we get the profile of a person standing side on? No, it's not. It's about how energy changes within a chemical reaction, and it's dealing with different types of graphs. Some people call it the hump graph, and maybe if that helps you remember it, that's good, but let's go and have a look at those energy profiles. And we can take some notes of different terms as well. So as you can see, the energy profile starts with some energy that's related to the reactants. Those are the things that we start with in a chemical reaction. So it's the beginning stuff. And these reactants all together have a certain amount of energy. In fact, this is chemical potential energy. And what happens is that during the course of the reaction, for different substances or different molecules, they'll have different amounts of energy. The energy changes. They don't all react at the same time. So during the reaction, the energy suddenly increases. The potential energy increases. So there's an absorption of energy, and they reach this strange state here called an activated complex. And then there's a release of potential energy, and we get products being formed. Now, that energy profile is describing certain energy changes, as we can see as we move across this course of reaction. Now, remember, as I said to you, it's not time related, because molecule A might react with molecule B at the beginning, but 10 minutes into the reaction, you might get molecule X reacting with molecule Y, and it's going to follow the same pattern of energy changes. And so this is an overlapping energy picture of what's happening to all the molecules as we look at the course of reaction. Overall, at the end of the day, all the reactants are going to form products in most chemical reactions if we've got enough things going on, if we have an excess of one and there's no limiting reagent. Let's just have a more careful look at this energy profile, And we recognized that one of the key features was the heat of reaction, or enthalpy. Now, the heat of reaction is recognizing here as a definition. It's the energy that is absorbed or released in a chemical reaction. Now, if we want to be exact in terms of calculating this, it's the energy of the product minus the energy of the reactant. So let's go and look at that same energy profile and see what we've got here. So now let's go and apply this idea of heat of reaction to the energy profile and see exactly how we label it on the energy profile. So here you go. You can see we've got the energy of the product, which over here is quite low. So it's a small number. Whereas the energy of the reactant is a bigger number. It's big. So if we take the energy of the product and we subtract the energy of the reactant, over here you've got a small number minus a big number. That means that you're going to make this a negative number. And that's quite clear. The difference between the energy of the product and the energy of the reactant is this little bit shown here. And it's given the title of delta H because that's the symbol for heat of reaction or enthalpy. Now, in this case, we've shown why it's a negative. There's a very important term for that. We need to recognize when it's a negative delta H, then it's an exothermic reaction. Why do you think it's the word exothermic? Well, exo means giving out, like exit, and thermic means heat. So exo, out, heat, heat going out. And that's exactly what's happening here. If you look at the amount of energy that is released, the energy released from the activated complex all the way down to the product is much bigger than the energy that is absorbed. So in any reaction, we have energy absorbed and energy released. Overall, in this reaction, there's an overall release of energy. And that's why we could make that definition of heat of reaction as the energy that is either absorbed, the net energy, if you like, that's either absorbed or released. In this case, the net energy was released. But what about if it was absorbed? Well, let's go and just clarify that we've got this right. Exothermic reactions where the energy is given out, so that's released. Those are ones that release energy. Delta H is less than 0. But as I said, you can get ones that are absorbed. And here we've got them. They're called endothermic reactions. And notice what's different here. The energy of the product is now big, and the energy of the reactant is small. So the difference between these two is going to be positive. Okay? So this is a positive value. So when it's endothermic, we get a positive value, and we can see that the net energy that is absorbed is this amount. So that's how we define your heat of reaction. We're recognizing the difference between endothermic, exothermic. Let's just get the definition for endothermic very clearly written down for a minute. So endothermic reactions are reactions that absorb energy, and the delta H is greater than 0. You can, instead of saying heat of reaction, you can say delta H. It's fine. It's just a way of summarizing it, and we all know what that means. You can use those terms interchangeably. Right, let's have a look at one or two more terms. So activation energy is a thing that we've seen on the graph, but activation energy is the minimum energy that's needed for a reaction to take place. So if we look carefully, you'll see that that's the energy that is absorbed between the reactant, between where we have the reactant and this thing called the activated complex. And so it's very important also to define activated complex. But to do that, I want to just stop for a second and deal with collision theory. Now, collision theory is something that we use to explain what's happening in a chemical reaction. We're saying the particles, they could be atoms or molecules, so I'll just call them particles. They could be ions as well. The particles of the reactant, they are moving around either as gases or as liquid, as ions in solution. They're moving around. They have energy. So because of the kinetic model. And what we're saying is if the reactants move around enough and with enough energy, they will collide with each other and they will gain potential energy. They've got enough energy. As they come close together, they increase their potential energy, they collide, they form an unstable complex, an unstable state. If they get a favorable collision and everything works out, they've got overlapping electrons and new bonds form, old bonds break, then what we will get is products will form. But the in-between state between reactants and products is known as the activated complex. So when we think about this reaction, we're thinking about little molecules colliding with each other, and initially they have low potential energy, but as they get closer to each other, it's like them being pushed in a magnetic field or an electric field. Their potential energy increases, and over here, they actually form an unstable pair. And that unstable thing can fall apart to become what it was or to become something new, a new product. It is important to understand that there are these movements and energy transfers that are happening. And the in-between state is the activated complex. So we define an activated complex as an unstable transition state from reactant to product. I think you've got that very clearly sorted out. Now, one of the things that can help us reduce the energy that's required to make the activated complex. In other words, to reduce the activated energy, to make less energy of it, is the addition of a catalyst. You say, what's a catalyst? Well, maybe you remember it and maybe you've even heard it before. We hear it in adverts, we call them enzymes, and we recognize that things go better when we've got these special chemicals around. They serve a special job. A catalyst is a substance that increases the rate of a chemical reaction without itself undergoing a permanent change. And it does this by lowering the activation energy. And I'm going to write the shorthand for activation energy as EA there. So have a look now. You'll see there's the activated complex. Lots of energy required to get there. But if we add a catalyst, there's the activated complex. The activated energy, which was all of this, is now being reduced, and we've only got to put that amount of energy. So you can see it's a much better idea to work with a catalyst, because a catalyst gets things done with less energy. And because of the less energy, there are more effective collisions that are taking place in the same amount of time. If we've got more effective collisions, we're going to make more products. And as we're going to see just now, that's going to mean that the rate of reaction increases. So I think we've summarized really quite well the ideas of energy and change. I want you to make sure you learn those definitions, the keywords that we've gone over, and the energy profile is really important. So make sure you consolidate your revision as you're doing that and practice drawing energy profiles, recognizing what's going on, and I'm sure that these easy marks will all be yours in the bag when you do your test or exam. I think it's time to take a short break, and then we'll be back to look at rates of reaction.